My name's Anthony, and I'm presenting our work on a long horizon planning framework for manipulating rigid point cloud objects. So let's consider this task where a bimanual robot must move an object between two stable configurations on the table. Assume the robot is provided with a set of primitive manipulation skills, along with a high-level sequence of the skills that should be used to complete the task. With this information, a system must then decide how the robot should use the skills at each step to move the object to the goal. The long horizon nature of the task already presents some difficulties. However, we also assume that the 3D model of the manipulated object is not known, which creates many additional challenges for current approaches from task motion planning. With this in mind, our goal is to overcome these difficulties and enable both long-term planning and generalization to unknown objects. We propose a framework for planning manipulation sequences that solve these types of long horizon tasks when we are not provided with a 3D model of the object. Our framework operates directly with an object point cloud and reduces the complexity of long-term reasoning by searching in the abstract space of object subgoals rather than low-level actions. However, simply planning over subgoals doesn't solve everything. In general, it's still critical to produce subgoals that are reachable, and we must also still determine the robot actions that can enable reaching them. One insight we make use of to simplify the problem of obtaining sequences of robot actions that reach the subgoals is to assume objects are rigid and that the robot maintains a sticking contact with the object. These assumptions enable reasoning purely in the space of rigid transformations that represent subgoal transitions and initial contact configurations between the robot and the object. This is because if the contact sticks, then the object maintains a fixed configuration with respect to the robot during contact interactions. To realize the benefits of these assumptions, we borrow a set of primitive manipulation skills proposed in the recent work, which are designed to maintain a sticking contact with an object. The skills take in an initial contact configuration and a desired relative transformation to compute a corresponding robot motion. So planning with these skills can be achieved by searching in the space of subgoals and contact configurations. However, we must still deal with the issues of determining subgoals that are reachable using the skills, and selecting contacts on the object that satisfy our sticking assumption and enable reaching the subgoals. Typically, one might design samplers to restrict the search space over these parameters, using heuristics and prior knowledge about the object. However, this limits the ability to manipulate novel objects. Instead, we look to the successes of learning-based approaches that enable more broad generalization to novel objects by mapping sensory observations directly to robot actions. In this case, we train neural networks to generalize the capabilities of these skills so they can operate directly with point clouds and be integrated within our framework. Our key insight in this approach is to learn a model for each skill, which is trained to map an object point cloud to a distribution over subgoals that are likely to be reachable and over contacts that are likely to be compatible with the skills and enable reaching the sampled subgoals. We then integrate these samplers into a sampling-based planning algorithm to enable multi-step reasoning directly using the object point cloud. Our multi-step planning results show that our framework enables long horizon planning for a variety of plan skeletons with unseen cuboidal objects, and that our learned samplers enable more efficient planning than a baseline sampler that utilizes carefully designed heuristics. We also show that our framework can manipulate objects onto different placement surfaces. Here we show a 5-step plan found by our framework, where the robot manipulates the object up off of the table onto a shelf. Our other qualitative results show that our learned samplers, trained only on cuboids, can generalize beyond cuboids to novel classes of objects. And finally, that our framework can be used to manipulate objects in the real world. So overall, by leveraging our assumptions of rigid objects and sticking contact, and learning to sample feasible subgoals and contacts directly using point clouds, our framework combines the best of hierarchical planning with learning-based approaches to manipulation. On one hand, we generalize planning methods to operate directly with a perceptual object representation, while on the other hand, we're able to plan over long horizons, which remains challenging for end-to-end learning-based systems. For more information on our learning techniques, novel subgoal representation, and planning algorithm, please see our paper. Thank you.